So you looked at the first Chapter 2 video, and we defined our kinematic variables in that. We defined what was called displacement, delta x, and we said that that is our final position minus our initial position. How we got there didn't matter. It's strictly where we were at the final position minus our initial position. And once we define displacement, we define average velocity as our displacement over our time. And then we define instantaneous velocity as our instantaneous displacement over time. In other words, our infinitesimal dx displacement over our infinitesimal time dt. So the derivative of our position with respect to time. And then we define a quantity called acceleration, which is our change in velocity over our change in time. We didn't really say what acceleration means physically. Let's give you an example. Since it's our change in velocity over our change in time, anytime you change your velocity in an interval of time, you will have an acceleration. And really is associated, in a sense, with a concept that will come later called force. Anytime you feel a force, you are having a net acceleration. So if I were to get in my car, hit my accelerator all the way down to the floor, and I was pushed against the seat when I did so, at that moment, I am being accelerated. I have an acceleration, even though it's possible that my velocity at that moment is still zero. I haven't changed my velocity yet at that moment, but it is changing, and I do feel the force, I do feel the acceleration. So acceleration can be physically associated with feeling some kind of force. If I'm driving along and I'm going at 50 miles per hour and my speed doesn't change, so even though I'm pushing on what is called the accelerator, but if my actual speed doesn't change, then I have an acceleration of zero. All I'm doing by pushing on the accelerator is I'm trying to overcome friction, so I have to use gas to do that. But as far as physics is concerned, I'm actually not accelerating when my speed is still the same. Okay, so once I get that point through, we want to use these new variables in some very nice equations called the kinematic equations. There are going to be 5 of them, and these 5 equations are going to be so important for motion that you're going to want to memorize them. So we'll get right into it, but these will be equations that will pop up when you least expect them in life, in your coursework, in work. You'll want to have them ready in your mind at any particular time. So let's start with this. We're going to say that our initial time is 0. We're going to start our clock right at the moment of 0. And we're going to call our final time t. We're going to say our initial velocity is v naught. V sub 0. V naught means that's our initial velocity at time t equals 0. And then we'll just call our final velocity v. With this definition, then, our acceleration is our final velocity v minus our initial velocity v naught over our time, which is t minus 0. So we say acceleration equals v minus v naught over t. If I multiply both sides by t and add a v naught to both sides, I get my final velocity equals my initial velocity v naught plus acceleration times time. This is kinematic equation number 1. Final velocity equals initial velocity plus acceleration times time. How this might work, let's say I'm driving along at 50 miles per hour and I start increasing my speed at 2 miles per hour per second, and I do that for 5 seconds. So at the end of 5 seconds, I'm moving at 60 miles per hour. I went 50, 52, 54, 56, 58, 60, and did it in 5 seconds. So the velocity would be equal to my initial velocity, 50 miles per hour, plus my acceleration, 2 miles per hour per second, times 5 seconds, means I increased 10 miles per hour, and I have a final velocity of 60 miles per hour. So velocity equals initial velocity plus acceleration times time. If the acceleration is constant, and I start my time t at the beginning at 0, then it's true that my average velocity is equal to my initial velocity plus my final velocity divided by 2. Only for constant acceleration, but that's all we're going to deal with is constant acceleration. So we can say this. Average velocity is my initial plus final velocity divided by 2. Well, the way I've written it here is final velocity plus initial velocity divided by 2. And I know my displacement, by definition, is equal to my average velocity times time. So it's true that my displacement, delta x, is equal to 1/2 times my final velocity plus my initial velocity times time. In other words, my average velocity times time. This is kinematic equation number 2. In this equation, I have 4 kinematic variables. I have displacement, delta x, I have final velocity, I have initial velocity, and I have time. 4 kinematic variables, there will be 5 of them. 4 kinematic variables, and I'm missing the 5th one. And if you look back at equation number 1, there were 4 kinematic variables in that one as well, and I was missing one of them in that equation as well. If I take kinematic equation number 2 and I substitute in from kinematic equation number 1 for time, if I solved equation number 1 for time, I would get the time was equal to final velocity minus initial velocity divided by acceleration. So I have this. Displacement is equal to 1/2 final velocity plus initial velocity times final velocity minus initial velocity divided by acceleration. So I have v plus v naught times v minus v naught, which you could see as the factoring of the difference of squares. So mathematically, I can write this like this. Displacement equals the difference of squares, final velocity squared minus initial velocity squared, divided by 2a, 2 times acceleration. If I take this and multiply both sides by 2a, and then add a v naught squared both sides, a little bit of algebra. So I have 2a delta x equals v squared minus v naught squared. Now I'll add a v naught squared to both sides. I get this. Final velocity squared equals initial velocity squared plus 2 acceleration displacement delta x. This is kinematic equation number 3. In this equation, I have 4 kinematic variables. I have final velocity, initial velocity, acceleration, and displacement delta x. I'm missing the 5th variable, which would be time. If I were reading a problem and I were given 3 kinematic variables and I was asked for the 4th one, and time was never mentioned and never asked for, then this is the equation I want to use. In other words, if I'm dealing with 4 variables and I'm given 3 of them, I want to solve for the 4th one, and the 5th one, which in this case is time, is not asked for and not given, then I want to use this equation. So the way that the problem is worded and what is given to you in the problem will help determine which kinematic equation you wish to use. Take a look at this. If I take equation number 2 and I substitute into it for my final velocity from equation number 1. Equation number 1 was final velocity equals initial velocity plus acceleration times time. I'm going to substitute that in to kinematic equation number 2. And this is what I have. Displacement delta x is equal to 1/2 initial velocity plus acceleration times time plus initial velocity, all that times time. Or I can write this like this. Displacement delta x equals initial velocity v naught times time plus 1/2 acceleration times time squared. This is kinematic equation number 4. In this equation, I have 4 kinematic variables. I have displacement delta x, I have initial velocity, I have time, and I have acceleration. I do not have final velocity. So if my problem were worded and I was never given final velocity and it wasn't asked for, then I could use this equation to solve for my unknown. Or if I were given three of these particular variables, displacement, initial velocity, time, or acceleration, and I was asked for the fourth one, I would want to use this equation to solve for my unknown. You know, I know that displacement is equal to my final position minus my initial position, so let's rearrange this last equation in terms of my position as a function of time. My position x will equal my initial position x naught plus my initial velocity times time plus 1/2 acceleration times time squared. So all I've done is rearrange the delta to give my position as a function of time. Now we know that if I take the derivative of my position, I should get my velocity. So my velocity is the derivative of the position as a function of time. If I take the derivative of this first equation, the derivative of a constant x naught would be 0. The derivative of v naught t would just get rid of the t. And the derivative of 1/2 at squared, if I decrement the t squared, I'm going to end up with just a times t. So I have now that my velocity is equal to my initial velocity plus acceleration times time. In other words, if I take the derivative of basically kinematic equation number 4, I get kinematic equation number 1. How about that? Instantaneous velocity equals initial velocity plus acceleration times time. That was so much fun. Let's do it again. Let's take the derivative of this equation, the derivative of my velocity, which should be acceleration by definition. So acceleration is the derivative of my velocity with respect to time. The derivative as a function of time of v naught, which is a constant, should be 0. And then the derivative of a times t will just give me a. So I have acceleration equals acceleration. True. So that's cool. So I take the derivative of kinematic equation number 1, I get the definition of acceleration. Acceleration equals acceleration. If I were to take the derivative of this, acceleration being constant, I would get 0. And all that proves is that my acceleration is indeed constant for these equations. All right, we're still interested in the fifth kinematic equation. If I take equation number 2 and I substitute in for initial velocity from equation number 1, I solve equation number 1 and solve for initial velocity, which will be equal to final velocity minus acceleration times time. I get this expression. Displacement is equal to 1/2 final velocity plus final velocity minus acceleration times time. And if I multiply all that through, I get this. Displacement delta x is equal to final velocity times time minus 1/2 acceleration times time squared. This is kinematic equation number 5. And I'm missing initial velocity. So in terms of constant acceleration, my total displacement, delta x, which we're treating as a variable, it's truly my final minus my initial position, but I'm treating delta x as my variable. Initial velocity v naught, the final velocity v, and time t, we have 5 kinematic equations. The first one is final velocity equals initial velocity plus acceleration times time. Of the 5 possible kinematic variables, delta x, acceleration time, final velocity, initial velocity, this one has 4 of them. It is missing displacement delta x. If I have a problem and displacement delta x is not given and is not asked for, then maybe this is the equation I want to use. Maybe I'm given 3 of these variables and I'm asked to solve for the 4th one. I want to use this equation. Kinematic equation number 2 is displacement is equal to average velocity times time And I can write average velocity as my final plus initial velocity divided by 2, since it's constant acceleration times time. In this equation, there are 4 kinematic variables: displacement, time, final velocity, and initial velocity. I'm missing acceleration. So if I'm given a problem and acceleration is not mentioned and not given, then I want to use this equation. Kinematic equation number 3, final velocity squared equals initial velocity squared plus 2 times acceleration, displacement, delta x. Of the 5 kinematic variables, this one is missing time. So if I have a problem, time's not mentioned, not asked for, not given, then I want to use this equation and solve for the unknown. Kinematic equation number 4, displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. Of the 5 kinematic variables, I'm missing final velocity. And we can guess, for our last equation, I should be missing initial velocity, and I am. My final kinematic equation is displacement equals final velocity times time minus 1/2 acceleration times time squared. Note for these final 2 equations that every term in the equation has the same dimension. Displacement has dimension of meters. Velocity times time, if velocity is meters per second and time is seconds, velocity times time has dimension of meters. And 1/2 acceleration times time squared has dimension of meters as well. Acceleration is meters per second squared. Time is seconds. Square that gives me seconds squared. So acceleration times time squared gives me meters. So every term in this equation is the same. Meters equals meters minus meters or plus meters, depending on which one you're looking at. And that's true of all these equations. Every time you have a different portion of the equation, the units should be the same. So if you ever forget the structure of the equation, you can possibly use that idea of dimensionality to figure out what the structure is, because all the dimensions of every term should be the same. All right, so we got these 5 kinematic equations that you're going to know and love, and you're going to want to memorize these 5 equations because they'll come up again and again. Let's try a problem. Here's a jet plane problem. A jet plane lands with a velocity of 100 meters per second, can accelerate at a maximum rate of minus 5 meters per second squared as it comes to rest. From the instant it touches the runway, what is the minimum time needed before it stops? Well, let's look at this problem. Let's see what's given in this problem. It lands with a velocity of 100 meters per second. So at the beginning of our interval of time, it has a velocity of 100 meters per second. So that is our initial velocity. It can accelerate at a maximum rate of minus 5 meters per second squared. So we're given the acceleration automatically as a minus 5 meters per second squared. To do this problem, we need 3 kinematic variables. So we're looking at it and we see, well, it comes to rest. So our final velocity is going to be 0. It came to rest. It didn't tell us explicitly that our final velocity was 0. It just used the word rest. So that's how we know. So we have 3 kinematic variables given, and we want to know how long it takes before it stops. So that's the 4th variable that we're looking for. So we have displacement is not given and not asked for. Acceleration of minus 5 meters per second squared. T is asked for. Our final velocity is 0, and our initial velocity is 100 meters per second. So we have 3 kinematic variables and a 4th one that's asked for. Looking at this, I want the equation that has these 4 variables in it, and it looks like I need equation number 1. Final velocity equals initial velocity plus acceleration times time. In this equation, I have the 4 variables I need. The 5th variable, displacement, is not asked for and it's not given. It's not in this equation. I want to solve this equation for time. I may realize that my final velocity is 0, So I add a negative v naught to both sides, and my time will equal a negative v naught divided by acceleration. That will be a negative 100 divided by my acceleration, which was a negative 5. So I'll have a negative 100 over negative 5, or it'll take me 20 seconds to stop. If I come up with a negative value for my time, I know I did something wrong with my algebraic manipulation of the equation. So the fact that I came up with a positive value means I did everything right. So I need 20 seconds to stop. Can this plane land at a small airport where the runway is 0.8 kilometers long? Well, now I know 4 kinematic variables. So if I'm looking for what the displacement over this time interval will be, I can use any one of 4 equations to find it now, because I know the other 4 variables, and displacement is involved in 4 kinematic equations. So that's good. Well, let's approach this from the standpoint that I didn't know about the time, because I solved for the time. I might have made a mistake in part A, and then I would just propagate that error in part B if I used that result. So let's pretend like we didn't know about time, and so we're going to use kinematic equation number 3 to solve for displacement. Again, I know my final velocity is going to be 0, so the v squared is going to be 0. I'm going to add a negative v naught squared to both sides, divide by 2a to get my displacement. So in this case, delta x will equal a negative v naught squared divided by 2a, which would be a negative 100 squared divided by 2 times the acceleration, a negative 5. That'll be a negative 10,000 over a negative 10, which will give me 1,000 meters. So to land this plane, I need 1,000 meters or 1 kilometer to land. However, the airport's only 0.8 kilometers long, 800 meters. So I would not be able to land this airplane at this airport. So as I'm landing this plane and I'm about to land, I make this calculation in my head. If I land at 100 meters per second and it's going to deaccelerate at minus 5, I'm going to need a kilometer to land, and I can't do it at this airport. So I pull up and I attempt to land at a different airport. Gives you more respect for what pilots have to do on the fly, so to speak. They have to make this calculation right away before they land, so that they know that they have enough distance to land. Maybe. Let's try another problem. In 1865, Jules Verne proposed sending men to the moon by firing a space capsule from a 220-meter long cannon with a final velocity of 10.97 kilometers per second. What would have been the unrealistically large acceleration experienced by the space travelers during this launch? Compare your answer with a free fall acceleration of 9.8 meters per second squared. All right, so Jules Verne wrote all these scientific novels back in the 1800s, and he was quite intelligent in the way that he approached the science. He did 20,000 Leagues Under the Sea, and he wrote, To the Moon. So, in this particular case, he's shooting our astronauts through a cannon, and we want to calculate what the acceleration would be. We know that the cannon is 220 meters long, so we're going to have to accelerate over that interval of distance, and so our displacement is going to be 220 meters. We want a final velocity of 10.97 kilometers per second. We're starting from rest, so our initial velocity is 0, and we want to calculate acceleration. So based on that, knowing our final velocity, knowing our initial velocity, knowing our displacement, solving for acceleration, we're going to use kinematic equation number 3. Time was never mentioned and not asked for in this problem. So we're going to use kinematic equation number 3, realizing that our initial velocity is 0. We started from rest. So solve this for acceleration. Divide both sides by 2 delta x. and we get that acceleration should be our final velocity squared divided by 2 times delta x. Our final velocity is 10.97 kilometers per second, so that's times 10 to the 3 meters per second. Square that over 2 times 220 meters, which will give us an acceleration of 2.735 times 10 to the 5 meters per second squared. That is 273,500 meters per second squared. Since the acceleration of gravity is 9.8 meters per second squared, approximately 10, this turns out to be 2.79 times 10 to the 4 Gs, or approximately 27,900 Gs of acceleration. That's a lot. That pretty much, there's no question, no one could survive that. The astronauts that we have today, who actually go through quite a bit of acceleration, maybe experience at most 9 Gs. I think most of the time they try to get in the range of between 3 and 7 Gs. And if they go in one of those cyclotrons or centrifuges that you might see at the Space and Rocket Center, you might experience 3 Gs in that centrifuge. But 27,900 Gs, no. So, in the story of To the Moon by Jules Verne, they take off and they go through this large acceleration, and it turns out that they had a dog on the spacecraft, and the dog didn't survive the takeoff. The acceleration was too great, and poor Rover died. So they had a little funeral, and they jettisoned Rover out into space. The problem was they were already in space, moving with a constant velocity through space, and Rover, once he was jettisoned, had the same velocity as the spacecraft. So as they're traveling to the moon, Rover and the spacecraft are traveling at the same speed. So as they're looking out the window, there's Rover, and he's traveling at the same speed as the spacecraft, so they had to look at Rover the whole time as they're traveling on their way to the moon. So very, very unfortunate. Sorry to end with that little story. Here's Colonel Stapp, and this is his reaction when I announced a pop quiz in the class. Wasn't too happy. Actually, Colonel Stapp was a volunteer who went through acceleration measurements back in the 1950s, and he was on this sled that was going pretty fast, and they stopped over a quarter-mile distance, and because of the impact of the stop, he actually was one person who experienced 23 Gs of acceleration. Because of this experience, all the capillaries in his eyeballs exploded, and he wasn't able to see for about 2 or 3 days before they finally recovered and was able to regain his sight. Nobody else has tried to beat his record. I don't know why, but the record is 23 Gs experienced by Colonel Stapp in the 1950s. Okay.